This is the last PowerPoint lecture in Chapter 13, Kinetics, and this talks about how we can use the information we've learned how to get from kinetic studies to determine what we call the mechanism, or the step-by-step process through which chemical reactions occur. So a mechanism, again, are the step-by-step processes that reactants go through to reach products. So, for example, the overall reaction that we see written, okay, 2 reactants or more give a product or more, right? That doesn't tell you anything about the pathway. Now, it's possible that this reaction does occur in one step, A and B collide and give you C, but it's also possible that these go through a multitude of intermediate steps. So maybe A and B combine to give E first, and then E does something to give C. So that's the mechanism, the individual step-by-step procedures to get to the final product. The overall balanced reaction that we see doesn't give us any information about the step-by-step process. So there is some vocabulary that you should be familiar with when we're talking about mechanisms, and one is molecularity. So again, from the overall balanced reaction, you really can't tell anything. You don't know if A actually collides with B, or if perhaps A makes some intermediate, which then collides with B. The individual steps that make up a mechanism, so that would be this step and this step in my imaginary mechanism here, these are referred to as elementary steps. And for an elementary step, we know what happens on a molecular level. So, for example, I could tell you that the molecule A reacts to give the molecule E, and that's the first thing that happens in this chemical reaction. So you can speak with confidence about what things are happening on a molecular level. So let's look at the chart at the bottom. These are all elementary steps listed in this chart. In other words, they are individual steps of an overall mechanism. If there is only one reactant involved in an elementary step, like I said here, A miraculously turns into E, we call that a unimolecular reaction, unimolecular step. If there are 2 reactants involved in a particular step of a mechanism, then we would say it's bimolecular. We can also say, if it's an elementary step only, we can also say, well, in this step, it's bimolecular, and 2 reactants A collide with one another. Because the elementary steps, you can actually see which species is colliding / reacting with which other species. And because of that, because of the detail we know for an elementary step, we can write the rate law for that individual elementary step with the order simply by knowing an elementary step. Now remember, if you're given the overall reaction, A plus B gives C, you can't write a rate law directly from this, because you don't know if the reaction occurs in this one step as shown, or if it has several kind of hidden individual steps it goes through. And so you can't say anything specific about the kinetics until you gather experimental data. But in an elementary step, you can. Okay, you have a level of detail. Since we have 2 reactant molecules A that are reacting and it's an elementary step, we know that it's going to be bimolecular and second order in A. So let's just look at a couple examples of that. Here is an overall reaction. With study, more intense study, chemists have found that this particular reaction occurs in 2 steps, 2 elementary steps. That the first thing that happens is 2 nitrogen monoxide molecules collide Okay, it's a bimolecular elementary step to give an intermediate. Notice this doesn't show up as reactant or product, it's an intermediate. And we could write a rate law directly from every elementary step. So we would say the rate for this step 1 is, it's the same format where you have concentration of reactants, but in this case, and in this case only for elementary steps, you can use the fact, yes, I know it's bimolecular, the order is 2. So you can use the coefficients, again, only in elementary steps in a mechanism to come up with the rate law. And we can write the rate law for every single elementary step. So for step number 2, the rate law would be as follows. Okay. So this slide simply emphasizes what I just verbally described to you, is in that you can write a rate law for an elementary step directly from the equation for that elementary step. Okay, so coefficients do become exponents, orders of reaction, for elementary steps. One of the things we can do when we know the mechanism of an overall reaction is we can use that information about the individual elementary steps to determine the overall rate of reaction. So it turns out that there is almost always an elementary step that is slower than the other steps that may be involved of the mechanism. And for anybody who has run a relay race, your race is limited in its overall performance by the slowest runner, right? And so it's the same type of thing in a chemical reaction. The slowest step is going to be the rate determining step. Okay, so again, the slowest step in a mechanism of elementary steps is the rate determining step. So if we can find the rate law from the slowest step, we're good to go. We know the rate law for the overall experiment. So to summarize very simply, the rate of the rate determining step in the mechanism is the rate of the overall reaction. Let's do some examples. Let's look at an example of a proposed mechanism. So here's an overall reaction, and here is the experimentally determined rate law for the overall reaction. And here is the proposed mechanism. So I'm going to show you how you can verify that a mechanism fits, okay, with all the data you have for an overall reaction. But I do want to point out before I do that, that remember that the rate of a reaction is dependent on the activation energy, and that the higher the activation energy is, the slower the rate, right? Because it's more difficult to get over that hump. Okay, so high activation energy has a slower rate. So each step in a mechanism has its own, it's not always shown as each step, but each step does have its own little reaction profile. And so if you do see a reaction profile with multiple humps on it, like this one, that is showing you the individual mechanistic steps. So according to this reaction profile, since step 2 has a lower activation energy, what does that say about its rate? The rate of step 2 is faster, right, than the rate of step 1 because it's an easier hill to climb, so to speak. Does this graph of data fit with the proposed mechanism? It does, actually very nicely, because in this graph it shows step 1 as being rate determining, or the slowest step, and that's exactly what the mechanism is consistent with. It shows that step 1 is the slow rate determining step. Continuing to look at the reaction that was presented in the previous slide, here's the overall reaction again. Here is the proposed mechanism. There are two requirements that must be made in order for a proposed mechanism to be compatible for the reaction given. And number one, when you add up the individual steps that are proposed in a mechanism for an overall reaction, the reactants and products must add up to equal the balanced reaction. So let's see what the heck I'm talking about here. So we're literally going to add up, and if you remember Hess's law, right, we add equations. We are literally going to add these two mechanisms steps together. So just as with Hess's law, we are going to combine all the reactants on the left-hand side from both or all steps of the mechanism. And then combine all the products together on the right side. And then you're going to cross out what's the same on both sides. So one of the NO2 goes, and NO3 goes. And what we are left with is NO2 plus carbon monoxide gives nitrogen monoxide plus CO2. So that's the first requirement that they add together to give the overall reaction. And you're going to want to compare then this to the overall reaction, make sure that they are the same. And the second requirement that must occur is the rate law of the slower rate determining step in the mechanism determines the overall rate law. So in other words, the rate law we would get from the slow step is the rate law for the reaction. So let's see what we get here. All right. Here's the rate law for the slow step. And now look for the experimentally determined rate law for the overall reaction. They are in fact equal. So this mechanism matches the requirements, and it is very likely the actual mechanism. The last thing I want to cover in mechanisms is to make sure that you are able to identify an intermediate. An intermediate, let me just clarify. Here's the overall reaction. Here's the proposed mechanism. An intermediate is a substance that is made during the reaction and also consumed during the reaction. So it does not show up, an intermediate does not show up in the original reactants, and it does not show up in the products. Okay, it only shows up in the mechanism, which means it is made and consumed during the reaction. To find the intermediates, let's look at the mechanism for substances that are formed during the reaction and then disappear, get used up again during the reaction. Okay, so I start looking at step number one. I look at those products to see if they show up in the final overall reaction. Okay, and HCl does, okay, which means it is not an intermediate, it's a product. So it looks like it may be HI. Maybe HI is an intermediate. So let's go to the second step of the mechanism and see if, in fact, HI is consumed. Yes, as a matter of fact, the second step of the mechanism actually uses this intermediate HI to react more with ICl. And so HI is an intermediate, and I believe that should be the only one.